these direct samplers, right, that have been proposed by Carvalho and al. There's another direct sampler proposed in 2010. There's a Metropolis Hastings algorithm proposed by Mitsakakis and al. And those are all theoretically correct, except that they propose changing all three elements at once in one step. So they propose essentially changing all the three elements in psi in one step. So what that means is that you will be jumping around your target distribution, and even if you are at the point where you have a lot of probability, you cannot stick around that point and explore it more, because you'll be just jumping someplace else, right? So that makes them quite inefficient for large graphs. So instead, what we did is say, okay, let's just change one element at a time, and this turned out to be a very nice approach that scales. So what I show here are Monte Carlo estimates of the acceptance probabilities of the methods I described corresponding with the cycle graph, right? So just a graph that links vertices 1, 2, 2, 3, 3, 4, and so on until it gets back, right? So I chose the cycle graph because there's only one component. This graph cannot be further broken, and it's sparse, which means you have a lot of dependent elements in K, right? So I have this parameter that gives the amount with which I perturb a certain element, a certain free element in psi, and then I did this experiment for p equals 4 vertices, 6, 12, up to 20, right? So what you see here is that the acceptance rates remain pretty much the same in our modification of the sampler, sampler from the Jewish distribution, while for the other two methods, you see the acceptance rates go to 0. So you cannot use this other method. We'll have to go with ours in what follows.
So what's the importance of the acceptance probability? And what is that telling me, actually? If the acceptance probability stays the same, what does that mean? It means that
so say
around, obviously.
So how many, say yeah, you can move around, so you can move efficiently enough. So you can still move, but don't move too much, right? So say CWC, that's the one Carvalho method. See, this method jumps around too much, so and it's a direct sampler, so this means you'll need a very, very large number of samples before you accept one, right? So it works fine with smaller graphs, but it doesn't work fine with bigger graphs, such as the United States graph that involves 49 vertices and these big maximal prime components, right? So I mean, you know, this is a side point. You know, just an example of the sampling approaches that are involved in this work, right? So now let's step back and look at the conditional, the car models we introduced a bit earlier, right? So I showed you where this matrix DW come from. So that's the classical approach, right? So the x's will be random effects, right? That are going to follow this multivariate normal distribution where DW lives in the right space. So now in this approach that we are proposing, we'll just put DW one step down, and now DW will be a hyperparameter of a G-Wishart prior for the matrix K. So you see, so the G-Wishart prior gives me case precision matrices that live in the right space, and overall you'll get your a mixture, right? That will be much more flexible than the classical approach, right? So there are a lot of valuable papers that describe how to choose this matrix DW that depends on certain weights, and they put a lot of thought into that. So all those results are not lost. And they are not lost because all you do is move everything one step down, and then you obtain a prior specification that can still be used and is proper, right? So to contrast the classical approach and this new approach we are proposing, see, we can look at the corresponding conditionals, right? So now the parameterization of our conditional C involves elements of the precision matrix K. So the G-Wishart prior induces priors on the regression parameters that we have, right? So in the classical approach, see, that's how all those regressions look like. And they, again, depend on only two parameters, rho and tau. So that is very restrictive, right? While in our approach, things are not fixed anymore, right? And uncertainty is taken into account much better than before, while staying in the right space. In fact, staying in the right space is key in a Bayesian framework, because once you numerically go out of your target space, it's very hard to come back in, right? Are there any questions about, because it's, so see, it's a natural extension. And you would wonder how come, this connection between these two literatures hasn't occurred before, because it just falls into place naturally, right? So fine, yeah, sure.
Do you have to choose? Do you have to select your hyperpriors on the tau and the? Do you have your hyperpriors, right? So you'll have to put priors on them, right? Yeah. Right. But see, whatever priors you got to pick here, you can also stick them one level down, right? That's just fine, right? And what is delta? Delta, right? I haven't talked about that. So if you look back at the parameters of the definition of the G-Wishart, right? So you have two parameters, delta and D. In order for this distribution to be proper, delta needs to be greater than 2. So any number greater than 2 will work numerically, right? D only needs to be positive definite. So it doesn't have to live in that cone, right? So in fact, you see, when I look at this model, right, I don't need dW to actually be in that cone to create something consistent, right? I can choose to be consistent and use that kind of parameterization just to create links with what already exists there, right? So delta and D, see, delta can be thought of as a fictive prior sample size, right? So say for delta equals 3, the prior functions as if you would have one observed sample, right? And D can be thought of as the sample covariance matrix, right? So say if I say D is the identity matrix, I say that a priori everything is independent, and delta quantifies the strength of that assumption, right? Okay, so fine. Okay, what we really want to analyze are those matrices, right? So we had a 49 by 11 matrix, and we said we want row and column graphs. So far, what I gave you are just models for one dimension. Now let's see how we can construct models for matrix variate data, and that's precisely what I'm showing on this slide, right? So X is a matrix of dimensions PR by PC, 49 by 11, and I will work. That's the Kronecker product, right? So I will work with a row precision matrix and the column precision matrix, right? So the joint distribution of the elements of Y matrix, right, is just multivariate normal centered at 0, whose precision matrix is given by the Kronecker product of the row and column matrices, right? So now each row and column precision matrix must be consistent with a row and a column graph, right? So I can do that. So here then conditional independence relationships happen for rows and for columns, right? That's the interpretation of my graph. So absence or presence of edges in the row and column graphs represent conditional independence relationships either for rows or for the columns. What we need to be very careful here is the fact that this product, the Kronecker product, is not identified, right? So if we multiply with a constant the matrix, the column matrix, then you know the same. We must, and we divide with the same constant the elements of the row matrix, right? We get the same thing. So there are many ways to take into account. Take this into account, and one way is to simply fix one element of the column matrix to a certain value, right? So I agree, this doesn't have a clear interpretation. There are better ways that relates to imposing constraints on the trace of either the row or the column precision matrix. They're all equivalent, and well, it's been argued that those type of constraints are more interpretable, right? And so before we, for convenience, we chose to work with this type of constraint. Why? Because, well, the sampler we developed can take this constraint into consideration very easily, right? So we can use our sampler for the G-Wishart distribution to sequentially sample the column precision matrix and the row precision matrix, right, while taking into consideration that constraint, right? So that's our model, and that is the model we are going to use for the mortality count data I showed you before, right, as random effect. We will see that. However, before we move on, we need to I need to mention that, well, we don't necessarily need to have 2 dimensions. We can actually think about arrays of data that now extend to a 3rd dimension, say time, or a 4th dimension, say secondary or primary cancers, or any number of dimensions you want, right? So your data can come in the form of arrays with an arbitrary number of dimension L, and then at each dimension you can have any number of levels. So arrays of this kind can be modeled through a joint distribution in which you have precision matrices associated with each dimension, right? So of course this represents an assumption. See, there's a separability of effects across dimension assumption, right? But that assumption is effective because it reduces the number of parameters I need. And then I can enhance the interpretation of my models and the sparsity of my models by making each precision matrices to live in a certain cone corresponding with graphs that could be different at each level, right?